Allahumma salli ala Muhammadin an-nabiyil ummi wa ala alihi wa sallim taslima. Assalamu alaikum, dear students. Today we are going to study mean free path. Now what mean free path is? We have to understand mean free path, but before going to that, we have to understand the motion of molecules of a gas. As we know that the gas molecules are always in random motion. As you can see in the diagram. This diagram shows you the motion of a single molecule which is moving through the sample of a gas. All other molecules seems to be stationary, but they are not. They are also in motion, but we have presented the motion of a single molecule. As this molecule is moving, it collides with other molecules. As a result, it changes its speed and direction abruptly, as you can see in the diagram. Here you can see that it is moving in this direction, strikes with this molecule, changes the direction to the other side, again strikes over here, changes direction, again here, there. This is the way it is changing its direction and speed constantly. Between collisions, the molecule is moving in a straight line. As you can see that during each and every two collisions, the molecule is moving in a straight line. Mean free path describes this random motion of the molecules. The symbol of mean free path is lambda. We represented it with lambda. You can see this is a single molecule which is in a container where no other molecule is presented. As a result, you can see that this molecule is moving in a straight line. So the mean free path is the average distance traversed by a molecule between collisions. The molecules are moving in different directions. The path between two collisions is different every time. Here you can see a very small path. This is large enough. This is large. This is again large. This is very large. This is medium. This is medium. This is small. So all are different. That's why we have to find out the average of these collisions, these paths, these distances. First of all, we have to find out the variation, on which variables it depends. Number one, it varies inversely with N over V. It is the number of molecules per unit volume. Or in other words, you can say that the density of the molecules. If density is large, definitely there will be more collisions and mean free path will be smaller. If density is small, N over V is small, there will be less number of molecules and there will be less collision. As a result, the mean free path will be larger. The mean free path vary inversely with the size of the molecules. You can realize immediately if the size of the molecule is small, the collisions will be less. If size is large, the collision will be large or more. This means that it varies with their diameter. The size of the molecule basically represents the diameter of the molecule. Now you can imagine that if the molecules were points, they would never collide and the mean free path would be infinite. As you have seen in the previous figure. Look at this figure. If there is no other molecule, then it will not collide with any other molecule. It can roam here and there, but no collision with other molecules. So the mean free path will be infinite. But it is not the case in the real gases. In the real gases, there are molecules, there are collisions. As a result, there is a mean free path in each and every gas. Thus, the larger the molecules, the smaller the mean free path. It is clear enough. Now we have to move to the next thing. Which parameter of the molecule is responsible for these collisions? So this is the cross section of the molecule, not its diameter. Diameter is there, but cross section of a molecule determines the effective target area. So the expression for the mean free path does in fact becomes lambda equals to 1 over under root 2 pi d square n over v, where lambda is mean free path, under root 2 is the multiplication factor, pi d square is the area of cross section of the molecule, N over V is the number of molecules per unit volume. So this is the expression for the mean free path. Whenever you have to find out the mean free path of a molecule, you have to use this equation. So now we move to the reasons how this is possible. We have studied that the mean free path is inversely proportional to the number of molecules per unit volume. So that's why we got 1 over N over V. Other thing, I told you that it is inversely proportional to the cross-sectional area of the molecule. So this is pi d square. It is also inversely proportional. So when we remove proportionality sign, we got equal and constant. This is equal and this is constant. Under root 2 is the constant over here, the multiplication factor. Now we'll put our attention to a single molecule. We focus on a single molecule and assume that it is traveling with a constant speed v and that all the other molecules are at rest as we assumed earlier. The molecules are spheres of diameter d. You can see in the figure the molecules, these are the two molecules, they are having diameters d. Each molecule has a diameter of d represented by d. So the collision will take place when these two molecules collide with each other. As you can see in the figure, these are the two molecules colliding with each other. The collision is there. You can represent it d by other way like this, the center of this one, and you can add and find this is also d. Now what happened next? When you consider a single molecule to have a d and all other molecules to be point like this. This is the main molecule which has a radius d, not the diameter. The radius is d. Radius is half of the diameter. So what would be the diameter in this case? The diameter will be 2d because d is equals to 2r, r is d, so this is 2d, and the other molecules, all other molecules in the sample are considered as point molecules. So this is a point molecule M. When these two collide, what will happen? Again, the criteria will not be changed. Why? Because the point molecule will not have any effective diameter, so the criteria will remain the same. As our single molecule zigzags through the gas, as we have seen already in the figure number 1, it sweeps out a short cylinder of cross-sectional area pi d square between successive collisions. If we watch this molecule for a time interval t, it moves a distance v delta t, where v is the assumed speed. Thus, if we align all the short cylinders swept out in interval t, we form a composite cylinder, figure 5, of length v delta t and volume pi d square v delta t. This is the figure which give you the correct representation. The number of collisions that occur in time t is then equal to the number of point molecules that lie within this cylinder. This is obvious, as you know that the distance is given by s is equals to vt. So this is s, which is v delta t from here to here. The next one is n over v. When you write the equation for this, so for the whole cylinder, n over v times the volume of the cylinder, means we have to multiply n over v with the volume of the cylinder. And what is the volume? We will multiply n over v to get the total number of molecules in the total cylinder. So area of cross section is pi d square and the length is v delta t. So we'll multiply the number of molecules per unit volume with it and we get that total number of collisions in time t. The mean free path is the length of the path and of course the length of the cylinder, and we have to divide it by this number. As you can see in the next slide, look at this. Length of path during delta t divided by number of collisions in delta t. So what is the length of the path? You can see that in the previous picture. This is the length of the path, v delta t. And which one is the number of collisions? This total term, n over v pi d square v delta t. So we have to divide v delta t by all this. So you can see that in the next slide. V delta t divided by n over v pi d square v delta t cancels out with v delta t. As a result, we'll left with lambda equals to 1 over pi d square n over v. Now this is different from the first result. And what is the difference? Difference is of under root 2. Here we were having under root 2 pi d square n over v. But in equation 2 we are getting pi d square n over v. This equation is only approximate because it is based on the assumption that all the molecules except one are at rest. You can see that in driving this equation we assume that single molecule is moving, all other are at rest, and all other are point molecules. In fact, all the molecules are moving. When this is taken properly into account, equation 1 results. Means what? Whenever you consider all the particles are moving, you will get equation number 1. Here you assume that only one particle is moving. As a result, we got this equation number 2. And what's the difference between the two equations is of 1 over under root 2. The difference is 1 over under root 2. Now why that difference came and how this could be removed? We have to conclude by this that there are two variables. Basically the problem, the difference arises from this equation. Look at this equation. This one. We have cancelled out this v delta t by v delta t. This could be cancelled, yes, fine. But these two v's are different. This v is different from this v. Now how they are different? The v in the numerator is average velocity, the mean speed of the molecule relative to the container, whereas the v in the denominator is v relative velocity, the mean speed of our single molecule relative to the other molecules which are moving. So now the latter average speed that determines the number of collisions. When you relate these two velocities, you can see that this relative velocity is equals to under root 2 of the average velocity, and thus the factor under root 2 is very important, which is missing over there. So now we can conclude that this is the actual result for the mean free path. Now we move to the example of a mean free path, that how mean free path is different in different cases. Now we can take one example which gives you the idea that how mean free path is different for a same gas. For example, the mean free path of air molecules at sea level is about 0.1 millimeter. It is measured and it is 0.1 millimeter. Now when you move up at an altitude of 100 kilometer, the density of air has dropped. As a result, what happens? The mean free path rises, as we knew that the density is inversely proportional to the mean free path, the number of collisions. So the mean free path is drastically increased and it raises to 16 centimeter from 0.1 millimeter at the sea level. At an altitude of 100 kilometer, it converts to 16 centimeter. And furthermore, when you move to an altitude of 300 kilometer, you can find that the mean free path will be 20 kilometer, which is a very large amount. Now there is a research constraint. The people who are engaged in the study of physics and chemistry for the upper atmosphere in the laboratory, they found the unavailability of containers large enough to hold gas samples of different gases that simulate upper atmosphere. We'll meet in the next lecture. Allah Hafiz.